Good morning. I am going to discuss about the topic as VLSI Introduction. So, what is VLSI? Very large scale integration is the process of creating an integrated circuit by combining thousands of transistors into a single chip. So, VLSI began in the 1970s when the complex semiconductor and communication technologies were being developed. The microprocessor is the VLSI device. Before introduction of VLSI technologies, most IC had limited set of functions they could perform. So nowadays there is a system on chip and everything will be the next level of the VLSI. An electronic circuit might consist of CPU, ROM and RAM and other true logic. So VLSI let IC designers add all of this into a one chip. So the very large scale integration is the process of integrating or embedding hundreds of thousands of transistors on a single silicon semiconductor microchip. So VLSI technology was convinced into the late 1970s when the advanced level of computer processor microchips were under development. The VLSI is the successor to large scale integration, medium scale integration and small scale integration and various levels of technology also. Now, it is one of the mostly widely used technologies for the microchip processor, integrated into circuits, IC and component designing. It was initially designed to support hundreds of thousands of transistors gates on a microchip which was as 2012 exceeded several billion. All these transistors are remarkably integrated and embedded within a microchip that has shrunk over a time but still has the capacity to hold enormous amount of transistors. The first 1 megabyte RAM was built on a top of VLSI design principles, included more than 1 million transistors on a microchip die. Now these are some of the evaluations, integrated circuit classifications. The first one is SSI, second one is MSI, third one is LSI, fourth one is VLSI, and fifth one is ULSI, and sixth one is GLSI. SSI means small scale integration. It is generated year 1964. Total number of transistors is 1 to 10. Number of logic gates is 1 to 12. And medium scale integration 1968 implemented and 10 to 500 transistors. Number of logic gates is 13 to 99. LSI large scale integration year 1971. Number of transistors 500 to 20,000. Number of logic gates is 100 to 9,999. And VLSI very large scale integration 1980. Total number of transistors is 20,000 to 1 lakh transistors. And number of logic gates is 10,000 to 99,999. And ultra large scale integration, it was evaluated in 1984. Number of transistors is more than 1 lakh and number of logic gates is more than 1 lakh logic gates. And finally the GLSI, very large scale integration or giga large scale integration, implemented in year 2001, typically in the form of the billions of transistors range more than 1 million logic gates. Now why VLSI? Why we are opted for the VLSI? Because the integration improves the design. Lower parasitic, high speed. Lower parasitic, what is the meaning of lower parasitic? Parasitic means there is a delay. Suppose when you are designing a circuit having a resistance as well as capacitance as well as inductance. So in order to minimize the parasitic components or parasitic delay, you have to increase the speed. So that is why when you are designing the VLSI circuits, main objective is the lower parasitic. And so definitely speed will be increases, low power consumption, physically smaller, integration reduces the manufacturing cost, almost no manually assembling. And advantages. So VLSI has many advantages. Reduce size of circuits, reduces the effective cost of devices, increases the operating speed of circuits, requires less power than the discrete components, higher reliability, occupies relatively smaller area, because as our objective is as well as the VLSI has large so many advantages. The size should be reduced and the effective cost should be reduced. When your size reduces proportionately, the cost also reduces and the speed also increases. When size reduces proportionately, the delay also decreases, the speed also circuit also increases. It requires less power consumption. The main part is power should be less, and discrete components less power consumption than the discrete components, and high reliability occupies the relative smaller area. And VLSI application, VLSI is an implementation technology for electronic circuitry, analog or digital. It is concerned with the forming pattern of integrated switches and gates on a surface of the critical semiconductor, microprocessor, personal computer, microcontroller, memory, DRAM and SRAM, special purpose process, ASIC and CD players, DSP applications, optical switches. As a many highly sophisticated control system, mass producible, and therefore it is cheap. And so applications are voice and data communication network, digital signal processing, computers, commercial electronics, nowadays e-commerce, automobiles, medicines and many more. So these are the VLSI chips. Here it is contained the different diagrams. These are the different VLSI chips based on our requirement as well as customer requirement. We have to design, and this will be implemented in a particular circuit or application oriented circuits. So these are the three different VLSI chips. Now the design of VLSI circuit. The first the flow chart is given. The first one is requirement study, and the second one is specification, third one implementation and validation and market. What is one by requirement study? The reason is requirement study means suppose the customer have some requirements. So that requirement, based on that requirement, you have to study what are the needs, what are the components will be needed, what are the process will be needed, what are the application oriented ways it is needed. Everything you have to analyze, and that is why first topic is nothing but a requirement study. And after that, specifications. Specification means when you find out the requirement study or note out this requirement study, after that you have to find out the specification for a particular components that you have to find out deep, and next you have to implement. So once you study the requirement, after that you have to find out the specification. Then next level is you go for the implementation process. Implementation process, you have to synchronize with a particular devices. So that time the specification should be perfectly matched. Otherwise the implementation part will be failure. So in order to synchronize properly, you have to fit or you have to purchase a suitable component for a particular requirement as well as particular application or particular circuits. And validation. So when you have to implement that, after that it is validated. So it will be used for such a long duration, or maybe this can be implemented in a particular this circuit or that circuit. So like that you have to validate that this will be sustained for a maybe 1 year or maybe a lifelong or maybe a particular duration. So you have to particular design engineer should validate that, then only the people of the market will be accept our product, and finally we have to send it to a market. So market, we know that already we are collected data from the customer. So based on the customer requirements, we have to design a components. So it will be properly synchronized with that. So that is why these are the 5 steps when you are designing a VLSI circuits. First one is requirement study, second one is the specification of the product, third one is the implementation part, and fourth one is the validate a particular product, and final one is a market. And VLSI design cycle. VLSI design cycle start with a formal specification of VLSI chip, follows a series of steps, and eventually produces a packaged chip. So it is nothing but a design cycle start with a formal specification. There is a specification is there, particular chip follows a series of steps. What are the steps you have to follow? Once we have to design a components, we have to so many steps. After that only you have to assemble the particular components, and finally you have to test it. So that is why it follows a series of steps and eventually produce a packaged chip. That is the final case of the particular design cycle. So this is the simplified VLSI design flow. The first one is the system specification, second one is the functional or architecture design, and third one is the functional verification, and the fourth one is the logic design and logic verification, and it is the next circuit design, circuit verification, physical design and physical verification. So first is system design specification. You have to collect the database from the customers as well as the designers will collect the database from the particular product, and you have to specify that. And from architecture design, you have to design your architecture and functional verification. Once you collect that, you have to verify that. And in logical design, you have to check the input. Based on the input, we have to verify the particular logic gates and logic verification. So these 5 things are the front end design, or we have to say it is nothing but a synthesis phase design or logic gate level representation. And the next one is the, suppose there is any deficiencies, any issues in the functional verification, again we have to recheck in the functional architecture design. So like that, logic verification also, if there is any issue, you have to recheck or you have to give the input vectors by assigning a logic design. So that is why there is a graph it is given. And next one is a circuit design, and after the front end design, it is move on to a circuit design and a circuit verification, and it is will be a physical design. After that, physical verification. So once you verify the logic verification, you move on to a circuit design, a circuit representation, and after designing a circuit, we have to verify the circuit whether what you design circuit should be functioning properly or not. And once you verify the circuits by using a tools, by using a log tools or maybe a Xilinx tools or maybe open source EDA tools, next we go for a physical design. So physical design also you have to first you represent the layout representation. So based on the layout representation, you have to design a physical design of a particular circuits, and after that physical verification, that is nothing but a DRC, design rule check. So by using a software, open source software, whether maybe a K layout or by different softwares will be there, or so many softwares will be there, layout softwares. Based on the layout softwares, we have to test the what you design the physical design. You have to test whether it is designed correctly or not. By using that software, or in the software there is a design rule check option will be there. That design rule check will verify that there is no corrections. If there is a no correction, finally the physically verified. That is layout phase. So in the simplified VLSI design flow, there is a 2 cases. One is front end design, another one is back end design. Front end design, we have to only the simulation part. Back end design, whatever you simulated will be converted into a physical format. So that is about the layout of the page. Next, 4 levels of design representation. First, behavioral representation, that is nothing but a gate and in forms of 3 column array format, and the second one is a logic gate level, and third one is a circuit transistor level representation, and fourth one is a layout representation. Behavioral representation, it is given as there is a 3:0 as well as 3:0 is given, and the control input, and there is an output. Here logical level, gate level representation, here we are taking the sum and carry, there is a full adder, there is a 3 input, and there is a 2 output, sum and carry. And so based on the 3 input, the output will be only 2. So here there is a functional block. By using the functional block, we have to simulate that. So FSM means nothing but a finite state machines, logic blocks and some gate. Next is nothing but a circuit transistor level representation. So this is nothing but once you design a circuits, you have to, this is the transistor schematics. So you have to design a single gate by there is a connections, arrangements. So circuit transistor level representation, you have to check by using a synthesized tools, whether may be a EDA open source tools, or maybe a Xilinx tool, or maybe a mentor graphics, whatever tools. By using these tools, you have to verify that the design circuits will be working properly or not. And if it working properly, we move on to next level for layout. Next one is the layout representation. Here layout representation, we previously see that there is a different type of software, K layout software. By using a software, you have to design. So this is the physical devices. So these are the 4 levels of design representation. First one is a behavioral representation. What are the gates needed? We have to represent in a behavioral form and a representation form. Next one is a logical level, and third one is circuit level and layout representation. Next VLSI design flow. Here there is a system specification, and second one is a functional arithmetic design, and third one is a functional verification and logic design, logic verification, circuit design, circuit verification, physical design, layout verification. So fabrication and testing. So VLSI design flow, there is a behavioral level representation, logic level representation, circuit level representation, logic representation. Previously what you were given is there is only the block diagram. Here how it is functioning, here by using a flow chart. The first one, there is a block called as system specification. So based on the system specification, we move on to a functional or architectural design, and after that we move on to a functional verification. Once you design a functional design, you have to verify the functional design by using a tool, and after that there is a logic design. Logic design, once you design a logic design, you have to verify the logic verification circuit by using a tools. And the circuit design, once you design a circuits, you have to verify using a circuit verification method, and after that physical design, and finally there is a layout. So first system specification, you have to design a functional design. So after that functional verification. So if there is any error in the functional verification, you have to recheck by using a functional design. That is why here it is a rechecking. So like that, here there is a logic verification also. If there is any issues or problem arises, you have to recheck the logical design, whether the input is or maybe high impedance or the value is coming. You have to recheck that whether a designed logic circuit is working properly or not, or maybe it is correct or not. You have to check. That is why there is a checking like that. The arrow is, there is a loop connected like this. And third one is a circuit design. Once you design a circuits and you have to verify that also there is a loop will be there. So what happens once you verify that, if there is any issues or problem, you have to recheck the circuits whether circuit is design, what you design is correct or wrong. And like that layout verification also we have to check. Once you verify the DRC, if there is a issues in the DRC, you have to modify the design or modify the physical design. So these are some of the flow charts for the VLSI design flow. Next there is a design methodology. There are 2 basic types of digital design methodology: top-down design methodology, bottom-up design methodology. So now here top-down design methodology, define a top-level block, identify the sub-blocks, divide sub-blocks until we come to a leaf cell. So the concept is nothing but, so here count is nothing but, there is a first one is a top-level design. Based on the top-level design, so many sub-blocks will be there. Based on the sub-block, there is a basic level will be there, or basic level will be there, cell will be there. From the basic cell, we have to bring in the top-down design methodology. And next one is a bottom-up design methodology. We start from bottom, that is leaf design or cell design. identify the building block that are available as far as build a bigger cells using this block, continuous build cell until we build top level. Combination of top down and bottom up design are used today is the digital design. So this is the block diagram, top down design methodology. This is the top level block. It is divided into 3 sub blocks, sub block 1, sub block 2 and sub block 3. And sub block 1 is divided into 2 cells, leaf cell 1 and leaf cell 2. Like that, sub block 2 is divided into 2, leaf cell 3 and leaf cell 4. As well as sub block 3 also divided into 2, leaf cell 5 and leaf cell 6. So this is the top level block. So when the top level idea is given, based on the top level idea, we have to divide into 3 category or 3 sub blocks. From the 3 sub blocks, it is divided into so many leaf cells. So this is leaf cells nothing but basic levels. So this is nothing but so there is a from the top level to you have to come to a lower level. Next nothing but a bottom up design. So first we have to design a cell or leaf cell. So each 2 leaf cell will be connected to a macro cell, and like that again this will be connected to another macro cell, another macro cell. Finally there is a top level block. So here bottom up design methodology, first we start from the leaf cell. From the leaf cell it will be connected to a sub blocks. After that it will be connected to a final level. So based on our application or design methodology or our customer requirements as well as our design concept, whether maybe they have to choose top level method or maybe a bottom up design method. And next is a simplified view of VLSI design flow. Here there is a top down algorithm, here is a bottom up algorithm, and here also there is a same the flow chart will be the simplified specifications and functional and architectural design, etc. And next one is nothing but Y chart. So what is nothing but Y chart? So it is nothing but a chart given up. There is a divided into a 3 category or 3 part. So first one is a behavioral domain, second one is a structural domain, third one is the geometrical layout. In behavioral domain, the Boolean equation, first one, modulus description, finite state machine, algorithm. So when in the behavior domain, what are the concepts, what are the things? First one is the Boolean equations. From the Boolean equation, you have to bring in the model description. From the model description, you have to bring in the finite state machine. So like that, structural domain, the basic cell is nothing but transistor. From the transistor to a leaf cell, from the leaf cell to register, from the register to processor. So the basic level for the structural domain is nothing but transistors, and after that from the transistor there is a leaf cell. Leaf cell consists of so many transistors, and registers consist of group of leaf cells as well as transistor, make it as a register, and finally there is a processor. And geometrical layout design, here there is a chip floor plan and model placement, cell placement and mask. So the basic nothing but a mask. After that there is a cell placement, after that model placement, after that chip floor plan. So next is system specification. The first step of design process is to lay down the specification of the system. First step to design process is lay down specification of the system. You have to find out the specification of particular system. Suppose if you want to go into a system or a chip, you have to know what is the design process, what is the specification required for particular processor or maybe a design component. High level representation of the systems and factors considered: performance, functionality, physical dimension, design, technique and fabrication technology. It is a compromise between market requirements, technological and economical viability. Next, the end results of the specification of the size, speed, power and functionality of the VLSI system basic architecture. So when you are design as per the specification, the size should be reduced, proportionately speed should be increases, proportionately power consumption should be reduced, and functionality of VLSI system should be working proper. Otherwise, there is a issues will be coming. So this then I have to find out the basic architecture. So next, functional design. The main functional unit interconnect requirements of system are identified. The functional design, your main idea is area, power and other parameters of each unit are estimated. The key idea is to specify behavior in terms of input, output, timing of each unit. So when you are designing a circuit, we must familiar about the input, output as well as timing of the particular function of a particular unit. The outcome of a functional design is usually a timing diagram. So based on timing diagram only, output will be working. This information leads to a improvement of overall design and process and reduction of complexity of the subsequent phases. Next, logic design. Design of logic, that is the Boolean expression, word, width, register allocation, etc. So when you are going to get logic design, you should familiar about the logic as well as Boolean expression. So based on the Boolean expression will be the logic design will be functioning, and the outcome is called RTL. What is meant by RTL? Register transfer level description. So RTL is expressed in a HDL, hardware description language, such as VHDL, very high speed hardware, high speed circuit hardware description language, and Verilog. And circuit design, the purpose of circuit design is to develop a circuit representation based on the logic design. So once circuit design is to develop a circuit representation based on the logic designs. Once you frame a logic design, based on the logic design, you have to frame a circuit. Boolean expression can be converted into a circuit representation by taking into consideration the speed and power requirements of the original design. So the Boolean expression can be converted into a circuit representation by consideration of the speed. When you design a Boolean expression, as per the Boolean expression, sometime there is a power requirements will be varying, as will be speed will be varying. So the Boolean expression, you have to minimize the Boolean expression, then only you have to design a circuit. If you design such a method, definitely the power will be reduces and proportionately the speed also increases. Design circuit including gates, transistors, interconnection, etc. Outcome is called the next list. When you are designing a circuit, it includes the number of gates, number of transistors, number of interconnections made on a particular transistors or particular gates. That outcome we have to define is called as the netlist. And circuit simulation is used to verify the correctness of a timing of the component. So when you are applying a circuit simulation for a particular circuit simulation will do verify whether the correctness or the timing of the components. So this is the circuit given here. What is given? Nothing but a back-to-back connection of the transistor NAND gate, and will be finally there is a output will be conducted a NAND gate. So when you are simulating these circuits, we have to give the proper input and proportionately we will get the output. And physical design. So this is the circuit, this is the layout given as 2 input gate non-NAND gate, 2 input NAND gate layout. The top one there is a blue color VDD supply. Here bottom there is a blue color VSS supply, and there is a yellow color. Here it is a P diffusion, and here bottom there is a green color N diffusion. So yellow color Q diffusion. So now when you are 2 input NAND gate, when you are designing by using a CMOS, then it's a dot B the whole bar. The equation is, so it is a dot operation. What happens? So NMOS would be series, and PMOS should be parallel. So here there is a n divisions and there is a two metal gate metal. It is nothing but there is nothing but a pink color. This pink color will be connected in series, and the top there is a P division, and P division there is a pink color, there is a K gate metal. So here there is two transistors will be connected in series, and the top there is a P transistors connected in parallel. So this is about the two input NAND gate, and overall design process. So there is a first one is a designer, then one is a task, and third one is a tools. So designer, there is an architecture and logical designer, circuit designer, physical designer. Task, define overall chip, RTL model, initial core plan, and behavioral simulation, logic, this is behavioral simulation, logic simulation, synthesis, data path, and schematics. Circuit designer, cell libraries, circuit schematics, circuit simulation, Gaussian blocks, and physical design, layout, and floor plan, place and route, parasitic extraction, DRC, and DRC. And tools, there is a text editor, C compiler, RTL simulator, register transformer, synthesis tools, timing analyzer, power estimation, and schematic editor, circuit simulator, router, place route tools, physical design and evaluation tool. So now overall design process, the architecture level, there is a three category: designer, task, and tools. So the architecture, what are the tasks and what are the tools required? Logic design, what are the tasks, what is tool required? Circuit design, what are the tasks and what is the tools required? Physical design, what are the tasks and what is the tools required for completing the particular design process. Next, in VLSI chip, we are familiar about that there is a small square of rectangular die less than 1 mm thickness, small die 1.5 mm into 1.5 mm near about or equal to 2.25 mm square, large die 15 mm into 15 mm 225 mm square. Larger die size means more logic, memory, and less poly. So this die contain more number of transistors at a time. They will be fabricated, and less poly, less yield. Dies are made up from the silicon substrate. Substrate provide a mechanical support, electrical common point. And the next one is the emergence of SOI technology. Here there is a single gate. SOI means silicon on insulator technology. So this is the single case silicon insulator device. After that, double gate silicon on insulator device. Nowadays there is a FinFET device, and nowadays multi-gate FinFET device. These are the emergence of SOI technology, silicon on insulator. So based on the requirement as well as circuit, as well as power requirement concept, as well as the designer's choice, whether we have to choose a single gate or maybe a double gate operation, or maybe a FinFET devices, or maybe a multi-gate FinFET devices. Next, the SOI device description. So this is the cutting section of the SOI device, silicon on insulator. So here there is a source, and here it is a drain N diffusion. There is nothing but partially there is substrate or buried SiO2 layer, and there is a gate layer here. Here SiO2 layer, insulating layer, and there is another gate material. So here it is nothing but a double gate operation. That is why here VG1, here another nothing but VG2. So this is nothing but a N channel device. N channel device. That is why here source is N diffusion N plus, and source is N plus, drain N plus. And below that there is a buried SiO2 layer, and here also another gate, back gate. So VG2 and VG1. So this diagram is nothing but P-channel device, SOI device, double gate. Here VG2 and here it is VG1. Here the P diffusion material, that is why source is P plus and drain is P plus, highly doped P plus and highly doped P drain, and here there is a substrate material is the N diffusion and SiO2 layer. After the oxide layer or insulating layer, after that there is a gate material VG1 and here another gate nothing but VG2. So there are three modes of operation: thick film partially doped, that is we called as PD, SOI, silicon on insulator. So there are three modes of operation: thick film partially doped, thin film fully depleted, and medium film SOI devices. So three modes of operation for the SOI devices: thick film partially doped and thin film fully depleted, and medium film SOI devices. So XD max, the DSI is less than XD max, greater than 2x D max. So here next SO types. So here nothing but the thin film SOI devices have the following properties. Here the low electric field, high transconductance, excellent short channel behavior, quasi ideal subthreshold slope. So now thin film SOI silicon devices have following properties: low electric field, it requires a low electric field, high transconductance and excellent short channel behavior. When the short channel behavior is excellent, what happens? The conducting behavior is very fast, it will be good performance, and quasi ideal subthreshold slope. And so this is about the diagram of partially depleted SOI, and this is nothing but fully depleted SOI. And SOI technologies versus conventional MOSFET. Advantages: SOI, lower parasitic capacitance due to isolation from the bulk silicon, which improves power consumption. This is due to lack of reverse bias junction in SOI devices. That means high frequency of operation possible with the SOI devices for same area power. High performance at equivalent VDD can work at lower VDDs. SOI devices have more flexibility and range in controlling its bulk potential, since there is no diode formed in the bulk. So bulk potential can vary from supply to ground, even more than that for both PMOS and NMOS. This means the body bias can be used very effectively to optimize power and performance. And third advantage: resistance to latch up due to complete isolation of the N and P well structures, and reduced temperature dependency due to no doping, better yield due to high density, better vapor utilization, lower leakage current due to isolation, thus high power efficiency, inherently radiation hardened and resistant to soft errors, thus reducing the need for the redundancy. So disadvantage is nothing but major problem of SOI silicon on insulator technology is self-heating due to poor thermal conductivity of the pyrene oxide. So that is the main disadvantage. So next, bulk CMOS versus SOI. In bulk CMOS, there is a complementary metal oxide semiconductor, that is threshold voltage varies with the channel length, poly etching variation cause threshold voltage variation must make the threshold voltage high enough to limit worst case sub-threshold leakage. What is meant by sub-threshold leakage? Sub-threshold leakage is nothing but there is a leakage between the before threshold voltage applying, so there is a small current passing from the source to drain, that we call as a sub-threshold leakage. So nominal VT is typically higher than needs to be, and SOI smaller threshold variation, nominal threshold voltage can be closer to worst case faster transistor, especially at low VDD. And sub-threshold behavior, bulk CMOS, sub-threshold slope, that is the threshold voltage of NMOS, logarithmic natural logarithm of 10, where VT is equal to KT by Q, thermal voltage is equal to thermal voltage 26 millivolt at room temperature, N is the process dependent, usually 1.5. So sub-threshold slope is about 90 MV volt per decade, and SY subthreshold slope of 75 to 85 millivolt per decade. Double gate MOSFET and FinFETs are the SY variation. Offer even lower subthreshold slopes. Gates around the channel turn off quicker. Here there is a comparison of the pulse CMOS and the FDI. So the more devices variably with the random dopant fluctuations, FDSY. This is the device variably due to the untopped channel, limited VDD scaling for low power, increased VDD scaling down, 0.4 voltage, high sensitivity to short channel effect, excellent SCE, and limited body bias capability, superior body bias capability, large junction capacitance for pulse CMOS, and FDSY, fully depleted silicon insulator, reduced junction capacitance, and prone to latch up, immune to latch up, and lower vapor cost, higher initial vapor cost for the fully depleted silicon insulator. Less complexity in system design, more complexity in for fully depleted silicon insulator. So this is nothing but a king effect. So the king effect is nothing but, so here when you are the king effect is occurring when is the partially depleted SOI devices. So this is the simulated graph for the king effect. Ion. So what is the impact of king effect devices? Is nothing but impact of ionization, hole injection in a floating substrate, forward bias diode, increase the floating body potential, reduce VTH, increase VT current. So Kim effect will be impact on the ionization as well as force injection, forward bias as well as the floating body potential. It reduces the VTH and increases the current. So these are the graphs partially depleted SOI devices, and partially depleted device, fully depleted silicon devices, and king effect. So this is nothing but a partially depleted SOI device. Here nothing but a fully depleted SOI device. So these are the graphs with drain current versus drain voltage. So the partially depleted, what happens is nothing but maximum 3 voltage. Due to king effect, what happens, the graph will be suddenly varying. But in case of fully depleted, the variation will be smooth. So that is the main difference. Here will be sudden variation due to the drain current as well as the drain voltage. And CMOS today, nowadays there is a CMOS of 5 nanometer technology. So 14 nanometer technology, effective length of the gate should be 20 nanometer, and in case of 5 nanometer, the effective length should be 10 to 12 nanometer. So now fin height with variation of large bulk FinFETs. So these are nothing but a FinFET diagram as well as bulk FinFET with the junction isolated diagram. So next, emerging the CMOS technology 5 nanometer beyond. Some of the challenges for the 5 nanometer node. First one is the electrostatic, second one is the parasitic capacitance, and third one is the leakage, and fourth one is the low voltage operation. Electrostatic is nothing but there is a capacitance when you are designing a circuits. When there is a gate material, there is a between gate material and the channel there is an oxide layer. Based on the oxide layer thickness, electrostatic will be varying, as well as parasitic capacitance of MOSFET will be varying. So this is nothing but parasitics. And leakage current, the threshold leakage current, so many leakage current will be happening, reverse leakage current. So low voltage operations. Low voltage operations means when it is operated at the low voltage, what is happening at the 5 nanometer will be there is a challenge. So this is the low voltage challenges. When you are taking this graph, here there is a threshold voltage, here it is a VDD, here it is a drain current. So this current will be starting from VDD to here ion, and there is a start from 0 to ion VDD. And low voltage application, same as it is VDD versus IDS. There is a graph. Here it is a red option on current, there is a FET, and a blue option there is a internal gain FET. And next we have to see about the some of the VLSI top companies, Texas Instruments. So, and this is the corporate in the United States, established in 1951. Analog Devices, it is in USA, established in 1965. And Cypress Semiconductor Corporation, established 1982, fully based on the semiconductor, and the company has total 14 design centers, more than 40 sales office, etc. And Broadcom Corporation, it is also in USA, 1991. And Cisco Systems, established 1984, and Bitmap Integration, it be established 1985. Next, Horizon Semiconductors in Bangalore in 1885, and 2D and 3D graphics, single chip, Blu-ray and transcoder encoder, and Inchipo Limited 1994, and semiconductor website. And Info Chips is one of the most trusted brands in product engineering and semiconductor services to aerospace, defense, energy, and healthcare, retail software, etc. And Trillion Tech Labs and corporate office New Delhi, and established in 2000. This lab is knowledge-based technology organization which offers electronic design solution. Company is leading computer-aided engineering provider. Reputed name, very large-scale integration company in India. HCL Technologies, Noida, Uttar Pradesh, established 1991. Business IT software, and here the headquartered in Noida, Uttar Pradesh. Company has an office in 26 countries worldwide, provide a support and consultancy industrial vertical including defense, aviation industry, energy, power, software manufacturing, semiconductor, and well-known name about VLSI company in India. That's all. Thank you.